There are entire courses all devoted to statistical quality control or statistical process control. Here, our real goal is just to get you introduced to one of those available tools, and that's the idea of a control chart, which was originally developed by a fellow by the last name of Shewart back in 1924. And so sometimes you'll hear these tools called the Shewart control charts, and interpretation of them, the Shewart rules. The certain aspects about these control charts are absolutely going to be related to the fact that these were developed back in this era when you didn't have digital computers available to you. So some of the ideas and approaches and ways to do things are geared towards what's the easiest way to process data by hand. And if these ideas had been developed at the same time digital computers were around, probably they would look a little bit different. And certainly they have advanced along the way, but there's a certain kind of historical use and understanding of the tool, and so there you can still see some of that lineage that's there as we develop these things called these control charts. We're going to focus back on the concrete production world, and in particular testing of the concrete of these 28-day specimens. Remember that we need 28 days for the concrete to gain strength to our target value, and we're going to take out an example from a recipe where the manufacturer, the producer, has a fairly confident understanding that the population mean is 5,800 pounds per square inch, and that the population standard deviation is relatively high at about 1,200 psi. That typically tends to often be the case with concrete, that it's just a more highly variable material from a natural kind of standpoint than, say, steel is. Right? Now, these control charts are a way to track what's happening as we produce different material, and there's various different kinds of control charts. This one is labeled as an X bar, which is just really a phonetic way of dealing with what we're really doing, which is a chart associated with a sample mean, or X bar. And the data that you see here is these little individual data points. One specific one is really a sample mean of some sort of subgroup. Right? So we've tested specific cylinders, and in this case we've compressed them, and oftentimes then that'll turn out to be only 3 in the concrete industry. In your other kinds of production industries, that sample size is oftentimes going to be up to about 4, 5, or 6. And of course, as a mean, then we want to divide by n. So even though it's one single data point, that's an aggregate data point representing samples that were all collected at one point in time. Right? And what you see referenced here is a subgroup, which we'll define a little bit more clearly in a moment. Right, now, the other aspect that you see here are these horizontal lines, a variety of different ones that you have at work here. The one that's right down the center is our center line of 5,800, and you'll notice that in this specific case that center line value is also the same as our population mean. And certainly in this case, since we know the population mean, that is exactly the case. In other control charts, that will be slightly different. It'll be an estimator of the population mean that will be our center line. These other two numbers at these outer bands are the upper and lower control limit, UCL and LCL. And in general, these control limits are going to be determined by a mean plus some number of standard deviations away from the mean. Now, the mean that we're talking about is associated not with the population mean, but really of what is it that we've got going on up here. And it's X bar, so so mu X bar plus K times sigma X bar. And that's a crucial key difference, just like when we were developing confidence intervals and hypothesis testing, understanding that right there, that's crucial. Right now, it's very common and most common here that k is going to be equal to 3 for that particular control limit. Right? And the control limits are really those outer bounds. Now, we also are oftentimes very interested in understanding what happens in these other closer regions. For instance, the 2 sigma or the 1 sigma, and of course on the other side minus 1 sigma and 2 sigma bounds are also of interest to us in trying to understand what the quality is and the control of the process. Now, if we find a point that is outside of this upper or lower control limit, out in here, we say that the process is statistically out of control. Right? And that's really the primary purpose of these, is trying to understand something about what's in control or out of control. So let's talk about that for just a moment. We go back to this view of the world that we have two types of variation. We have chance causes, sometimes also called common causes, and we have assignable causes for our variation. Now, some people don't like the word assignable and find it more useful to call them special causes. Another way to think about this is that the chance causes you could think of as sort of naturally occurring variability, and assignable causes in a sense being man-made or man-caused variability. So for instance, if we change source of raw material, then we might expect to see a significant change in our process, and so that's a man-made, man-caused variability that we would like to know for sure, and we'll talk a little bit about how we ought to control that and ways we can do that. Other man-made variability might be associated with, say, the wear of a tool, right? And so we might see drifts and change of what's happening in our process mean simply by that's related to an assignable cost, and that's one of the big reason that we're after or want to use these control charts, are to be able to detect the assignable or special causes. And how do we do that? Well, a lot of this is about developing rules to analyze the control chart. As well, it becomes also a matter of pattern recognition. So what I'm going to do here is I'm going to read off some of these rules to you, but so that you can see the graph as I read those to you. You also find these Western Electric rules in your Montgomery and Runker text. But one aspect to take note of is that every industry has perhaps their own set of specific rules that they follow, and so although they might be slightly different, they do have pretty much the same overall flavor at the end of the day. For instance, we've already mentioned one of them. That is, if one point plots outside of the 3 sigma bounds or control limits, then our process is statistically out of control. By the way, what some people will do sometimes is that they will, if you do have some out of there when they process the data, they'll say, hey, those are out of control. I don't want those to heavily influence my average. And we all know that averages can be heavily influenced by extremely large or small numbers, outliers, so to speak. Right? And so they'll go back and they'll exclude those to recalculate this, and that gets into a slightly different kind of X-bar control chart where we don't already know the mean and we don't already know the standard deviation. We'll get more into that in a bit later. So if one point plots outside the 3 sigma control limits, we're statistically out of control. That if we have 2 out of 3 consecutive points plot beyond a 2 sigma limit, so we're in this outer zone. Some people call this the zone A, B, and C, so this would be a zone C that we'd be talking about. So I'll write that down, A, B, and C. If we have 2 out of 3, well, we don't have that. We have 1, but out of those 3 consecutive, that's the only one there. And we don't get close in this particular case to any more. So we don't have to worry about that rule. And then the third rule is, well, what if we have 4 out of 5 consecutive points plot at a distance of 1 sigma or beyond from the center line? And so here's one that's outside the 1 sigma, and then we come along, here's another one, but out of the 5 there's only 2, and we need 4 out of 5, right? So going here, here's 5 and we get 2 of them, but okay, so that's not it. 1, 2, yeah, no, don't have to worry about it. And so it looks like, no, we don't have to worry about rule 3. And then finally, in terms of the Western Electric rules, there's, if you have 8 consecutive plots point on one side of the center line or another, you think that you might have a process that's statistically out of control. And the idea there is that if you have a whole bunch over here, that your process is potentially drifting, right? And that might be associated with a part wearing out on a machine that's doing a tooling or cutting something to a particular dimension. Right. The other aspect of this is to look for runs, and so if we have this consecutive run up, that sort of suggests that maybe there might be something going on. Same kind of thing here. Or if there's a cyclic pattern that periodically we come back to something over and over and over again, also sort of suggestive of something that's happened. So how do you know when it's just a natural kind of thing and when it's not? Well, if you think back to our linear regression models and we looked at plots of residuals, we'd like to see natural variability just sort of randomly plopping up and down on either side of our mean. And so that's one aspect. But we also need to know something about how things are being produced. And that will also guide us to how we define what we call these sort of rational subgroups of data. And so, for instance, in the production of concrete and how we actually do the sampling, this sample size of 3 is related to that when a truck delivers concrete, out of the middle portion of that volume of concrete, we're going to take 3 samples for testing. And we'll also take some other samples for other kinds of tests as well. But we tend to keep the sample size to be about 3 in that particular aspect. Now, we're not necessarily going to measure every single truck that's delivered to our site, but if we have a large construction project that might be going over many months, we might have some seasonal changes. And so what you'll see is that you'll want to be careful to think about how are we collecting data so that we're not potentially getting natural variability that's caused by something that is as simple as that the weather has changed. Right? That's assignable cause. Oh, wow. All right, so we got to be thinking about how we collect that data over that kind of a time frame. If you're in say a more common production environment of a piece that's coming off in you're producing, say, a small little spring, and that's going to go on to another part of the assembly line, and you're producing thousands of those during the day. Well, you might be collecting your samples, say, 6 times in an hour, and maybe it's you want a sample size of 6, and you do that over an hour. Well, you want to be thinking about, hey, when do you restock that process? How often do you have to go do a new batch of springs? And let that guide you perhaps in how you do the definition of a subgroup. And so that's a big thing here down here at the bottom when you have this little small bullet about rational subgroups. Your goal here is to isolate your chance causes versus your assignable causes. Don't mix in something that's could cause a change, such as a change in raw materials, or being careful to think about who's doing the operation of the production. Is this computer controlled or is this human controlled? And if it's human controlled, what element does fatigue potentially play, and how might that show up, and having some kind of a sense of being able to isolate that, so that when you come back to interpret any patterns or trends, that when things are showing up outside, that's really an assignable cause and not something that's really just natural variability. We're going to get into in a moment exactly why 3 is such an important number of standard deviations away from the mean, and why that's of such useful value to us from a statistical significance kind of perspective.